Today's lecture is on data cleaning. This is the most underrated process in all of stats, and it's one that you're really going to want to get good at for these independent projects because you want to find truth, and there's a lot of potential for error if you don't clean your data. Now, when I say clean your data, I'm talking about first and foremost, check for impossible answers and typos. And while it's not on this slide, you need to double check all your data at least 2, 3, 4 times. If I am taking data from a computer program or even from hard surveys, I am going to double, triple, quadruple check. I'm going to make 2 different data sets, make sure that they have the same exact numbers in them. I know it sounds like it's just a lot of extra work, but what I am certain of at the end of the day is that my numbers are correct and there aren't typos or impossible numbers in there. And if I find a problem between 2 data sets, I can then go back and look at the data and double check to make sure which one it is, and then do it one more time to make sure I get all the answers correct. That's a little extreme, but our data is the most important thing in the entire field of psychology. So we have to treat it with reverence. The second thing we want to do is we want to remove outliers. Outliers have a drastic impact on your mean calculation. And the same thing, the third thing we want to do is check for normality. And if we do not have normality in our data, if our data are not generally normal or sort of normal, then we need to transform it. Let me make this point again. Why are we doing this? Why should we clean our data? Well, first, I think the impossible scores, the incorrect scores, the typos, that's super clear. If you have an impossible score in your data, you're just adding error to your data set. And we've talked about this. Error in your data set is the worst thing you can have. Now, the other 2 factors, outliers and normality, having a non-normal distribution, will drastically pull your mean towards the outliers, towards the skew in the data. So you've seen this picture before. I'm going to go over it a little slow. So essentially, this is where the mode is. That is the point that is the center of our distribution. That is that point where we get that hump. This hump is what we really care about. We care what the number is at this hump. It is the center of our distribution, and it's what we want to get the estimate of. That's our signal. Look what happens to that signal when you have a skewed distribution, like a non-normal distribution. That signal is pulled towards the skew, towards the non-normality, towards the outliers, right? And that is a problem. It's going to drastically impact our measure of signal. This is why we get rid of outliers and we transform our distributions to be normal when they're not. This is very, very, very important, particularly in samples like yours that are extremely small. I want you to see this. This is the number we want to find. I know it says mode on here because the mode doesn't change, but this is really the number that we want. And when we have outliers present, our mean gets pulled drastically away from the signal that it truly is. So this is like a mean that is not actually accurately representing our mean, our signal, our score that we want to find. We want to get rid of these outliers. We want to get rid of non-normality so we can get the best estimate of our means, so we can get the best estimates of our signal. So let's just go to step 1, fixing impossible scores. I have a very simple data set here. It was a raw score self-reported stress where the highest possible score was a 6, not 100. So I see that I have 100 in this data set. I went back to my data. It was actually a 1. So I changed it in my data set. My next step I want to do is check for outliers. Now, I know another set of numbers came up. Just ignore this column of numbers. But essentially, I need to check for outliers. And how do we do that? Well, one of the things that I think is important to understand about statistics is we still argue about what we should do. And in the last 10-ish years, people have started using more and more the absolute deviation around the median, or the median absolute deviation. MAD is what we call it. So I just am showing you this article cover so that you see where my method is coming from. But I'm going to discuss this method. So MAD equals the median absolute deviation. And essentially, according to the MAD rules, if a score is 2.5 MADs devious from the median, it's an outlier. So what is a median absolute deviation? Let me go through the calculation process so it makes sense. Our first step, we have a series of raw scores, just like we did in the previous example. And what we do is we calculate the median. Now, this is finding the middle of our data set that is not affected by outliers. This is essentially our signal. So we're saying like the median is our signal. That's what these authors are saying. And why use the median, not the mean? Well, we've already seen that. That picture I showed you a few slides back, if we have outliers in a data set, the mean is going to be pulled away from that hump towards the outliers. So this whole method starts with the median. A lot of methods start with the mean, but as we have just discussed, the mean is drastically impacted by outliers. If it wasn't, I wouldn't make you do this, but I want you to find truth. So step number 1, find our median. And then in step number 2, we're basically doing that absolute deviation that we should have done for standard deviation, except we're taking the absolute deviation of each score from the median. So this tells us for each score the error in that individual score. Then we count and then we calculate the median of the absolute deviations from the median. So we take the errors in the previous step and we calculate the median of those errors. It's a lot of words to say, but essentially what's going on in this step is that I am just simply calculating the total, the median, the average error in this data set using medians instead of averages. I use the word average just so you could think about it in that way. I'm literally saying like, okay, on average, how much do scores deviate from the median? That's all I'm looking at here. Right? Those are all pretty simple. Those are all very similar to our method we used in standard deviation. There's one step in here that we're not going to understand because we're not statisticians. So the last step is you take that median of the absolute deviations from the median, the MAD, and you multiply it by 1.4826. This is necessary when we are assuming normality like we do in psychology, according to our math nerd friends who are helping us out. So this is something I'm not going to explain in depth, but they have done one of those studies where they test the efficacy of our statistics, and they found that, well, because we are assuming normality, we have to multiply our MAD from step 3 by 1.4826. So I'm going to go back to this again. Sorry for the email. If a single raw score is greater than 2.5 MADs devious from the sample median, it equals an outlier. So what do? We take the median of the raw scores minus our MAD calculated in that fourth step times 2.5. We take the median of our raw score. We add the MAD times 2.5. That gives us the lower limit and upper limits of our outlier definitions. Anything that is more extreme than these values, either more negative if the score is negative, or more positive if the end score is positive, right, or more towards the tails, you'd see it in a distribution, then we define it as an outlier. This is not something that you necessarily have to calculate. I've created an Excel file for you that I'm going to show you how to work. Okay, so I've told you the steps of calculating outliers from MAD, but essentially I've made a very easy to use Excel calculator that will help you out. Now, what I'm going to do first is just grab my data and then put it in that calculator. So that calculator, you will have access to it on World Class. I'll put it in its own folder. But right now, I want to grab my raw data here. So I'm grabbing that. I'm opening my Excel. I'm opening my median average deviation calculator, and I'm going to paste my raw numbers in. They were already in there. And what it does is it goes through all those steps and it just gives you simple output. Please remove me, I'm an outlier. And you can see up there that's kind of some complicated programming that goes into it, but essentially if it's an outlier, it tells you to remove it, and then that's your new data set, right? We've removed the outlier. This is our new data set. So these are the numbers I'm going to want to use in my next step. So that's essentially how you remove outliers. You use this simple to use Excel sheet that I created for you. You can save it, and you're using the MAD. But essentially, that's how it works, and it's pretty cool. Okay, so now I'm going back to the PowerPoint slide. I'm going to slideshow, play from the current slide. I'm going to pick, you can see what those numbers were now because I was practicing earlier. That's an outlier. Those are not outliers. Now, I have talked about this not too long ago. I'll show it again. I think it's a very important slide. When you have just like outliers pull the mean, when you have non-normal distributions, they ruin your mean estimate as well. We can see this in the examples of positive and negative skew. We can see how much the mean is pulled away from the hump. And the hump is what we're interested in. We want to know the hump. But look what happens when we have a symmetrical distribution. Mean, median, and mode are all identical, right? And so if we have a symmetrical distribution, our mean is much more closer to the true value. So based on these pictures and years and years and years of other statisticians doing this, we found that we get better, more truer estimates of your signal if the data are normally distributed. So how do we check for that? So how do we test for normality? Well, the way that is best for beginners to understand normality is to really estimate it with the quantile plot or the QQ plot. And essentially the question is simple. Is our data set normally distributed? Now this is our data set from the previous slides where we removed that outlier of 6, right? So what is a QQ plot? Well, one axis is super simple. It's a scatter plot with one very simple axis. It doesn't matter if it's the X or the Y either. You'll see that in a second. But one axis is just your raw scores listed from smallest to largest. So, you have to list your scores from smallest to largest. So in this case, we go to our data set 0, 0, 0, 1, 1, 1, 1, 2, 3, 4. So that's how we would list those numbers on the scatter plot. The second axis is more interesting and allows us to understand if our data are normally distributed. The first thing before I talk about that second axis is I want you to look at this normal curve. Now, this normal curve and all normal curves share the property where most of the scores are centered around the middle of the distribution, in this case 0. In most cases it's 0. Right? The center of that distribution, most of your scores are here. But you'll notice as we move out to the tails, the frequency of these scores become less and less and less likely. Less and less and less likely. So we're trying to check do our data meet this pattern where most of the scores are in the middle? And as we move to the tails of the distribution, do we find less and less and less numbers of scores? That's the basic idea. Does this data set on the left fit this distribution on the right? Now, how do we do that? We're going to take our normal curve and we're going to divide it into n number of equal sections. Now, when I'm saying equal sections, I'm talking about equals in terms of probability, not in terms of the number line. So, here we got the probability, this whole thing adds to 1. So we're going to split this up into 10 equal sections where each section has the same amount of probability in it, the same probability in it. It's the same size of probability, just like I was talking about before. And so I've done that right here. And what you can see is that I've created, now I may not be perfect. I should have done it with a computer, but I didn't have the time today. But I've broken this into 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 sections, right? Like this is 10, these are 10 equal sections. What you're not seeing is that, this goes on to negative infinity, this goes on to positive infinity, but, I am working with PowerPoint here. So these are 10 equal sections, not in terms of the number line, but in terms of probability. This has the same number, the same probability as this, which has the same probability as this, has the same probability as this section, and these sections as well. Okay? So, and it goes on for infinity. So we're saying this section in terms of probability is 0.1. This 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 is 0.1. 0.1, 0.1, 0.1, 0.1, 0.1. Essentially, that's what we're saying. Because we broke it up into 10 equal sections. But that's all we're doing. So my second axis then, right? My first axis has the raw scores listed from 0 to 4 in that order. But now this would be like negative 100, negative 2.5, negative 1.2, negative 0.5, negative 0.1, 0, 0.1, 0.25, 1.5, 2.25, whatever I said earlier, right? We've just broken it up into 10 specific points, right? 10 specific points on the normal curve, assuming that the normal curve, 10 different points in terms of probability, the probability of finding an observation, the number of observations, essentially, the number of potential observations in that specific area. These are all equal to each other. So yeah, I hope that makes sense. Let me try to describe it one more time because I know this is confusing. We are breaking this distribution into equal pieces based on the number of observations in those pieces. We're breaking them into 10 equal pieces because we have 10 observations in our data set. So we're trying to see, does our data set map onto a normal data set? And if you look here, right, if it did, our lowest number would be drastically lower than our next lowest number, which is a lot lower than this number, which is lower, but not a whole bunch lower than this number, which is a little bit lower than this number, but not much, right? This number's gonna be, all the other numbers are the same, just on the opposite side, so they're positive, okay? And we're just saying okay, if this data set is distributed normally, these are the values we would expect for each of these observations. And then we put these in a scatter plot. And what we've done is we've created an expectation for a linear relationship. That's what we've done. It's kind of hard to explain that piece if you don't get it already. But essentially what's going on here is if our data are normally distributed, right? If these data are normally distributed, we would expect a 1-to-1 correlation with these values on the normal curve. This number that's between 2 and 3, this number that's a little bit greater than -1, and so forth, and the numbers in our data set. If these numbers match up in a linear fashion, we have normality. And so here's just an example from a textbook. I've circled what I'm talking about. If we have a normal distribution, our sample quantiles, because that's what we call it, really it's just setting the raw scores from smallest to largest, but we're going to call them quantiles because that's what some stats nerd called it to confuse people, right? But these quantiles are going to be correlated with the theoretical quantiles from the normal distribution, okay? So that's how you check for normality theoretically, but how do you do it for real? So there are two ways you can use the internet, which is great, and you can use SPSS. I'm going to show you how to use both of those in a second. I'm going to exit out of the slideshow right now. I'm going to grab my data one more time. My data after I've removed the outlier, that's why it's over here. And I'm going to click here. I'm going to show you, well, how do I check for normality? By using the internet. So first thing, I click that link and it takes me to the tool that's going to allow me to calculate normality, calculate the QQ plot. So I enter in all that data from earlier. It's a small data set, but it's for illustration purposes. And all I have to do is hit this compute button. And what it does is it spits out a graph that you don't need to learn. You don't even need to worry about this one. And it spits out my QQ plot. And what you can see, like if this was a normal curve, we would expect these dots to be in one line. We're not seeing that. So our goal here is like, okay, we see we don't have normality. We're going to have to deal with that in the next section of the lecture. All right. Now, PSPP won't do it. The free version of SPSS won't do a QQ plot. That's why I found this internet site for you. I'm actually going to go ahead and copy this. I'm taking a screenshot. Command Control Shift 4 on Macs will do what I'm doing right here. And I'm going to create a new Word document. I'm just going to paste this in there, and it pasted it in there for me. Okay. So I'm just keeping that one in there. And now I'm going to show you how to do the same thing in SPSS. So you can see I've kind of been messing around here, and that's fine. I'll go ahead and delete these scores. But here we go. Here are our scores with the outliers removed. I'm going to click Analyze, Descriptive Statistics, QQ plot, quantile plot. I'm putting in my variable, normal distribution, estimate from my data. I'm just going to stick with their default blooms here. And then I click break ties arbitrarily. You are going to click that. I click that so that my two graphs would be very similar. So now I click OK. And I've had this open before. Now, the thing I hate about SPSS, gives you a bunch of stuff you don't need. Like, we don't need this plot right there, so I'm going to cut it just so it's not in the way. I do need this plot. And what you can see, and I'm just going to show it to you. I'm going to screenshot it, as before, Command Control Shift 4, and I'm going to paste that into that Word document here. And essentially they're the same graph, except if you look closely, you'll see that the expected normal values are flipped on the SPSS graph. They're on the y-axis. on the internet graph, they're on the x-axis. I don't really care which one you use, but we can see with both of these examples that you can also see it's the same graph too. If you're creative, you can kind of look and see that the numbers, you got these 4 points here, they're kind of turned. These 4 points are turned. You can see how the whole thing's just kind of turned. But essentially, we do not have normality. And so the question is, well, what do we do? So let's go back to our slideshow. So how do we correct non-normal data? There's lots of different transformations you can use. And today I'm only going to talk about one to keep it simple, but also this is the one that works the best for data in psychology in general. Now, what we do is we call it a natural log transformation or a natural log transform. I'm going to transform my data. Now, in order to understand this, you have to understand that there's a number in the world called E, which is 2.7182818288, keeps going. And it's just called the natural number. We'll just leave it there like E. It's the natural number. So if I want to take the natural log of a score X, I get the answer A, where e to the A power equals X, which is, it's kind of weird, but it's not that hard. It's just when I find the natural log of a score X, what I'm finding is the number where E 2.7182818828 to the A power equals X. Right? So if I wanted the natural log of 7, what I am going to get, what I'm looking for is the answer A, so which is e to the A power equals 7. So 2.7182 to the A power equals 7. So that's how the math works. So when we find the natural log of our score, we are simply finding E when taken to which exponent A results in the original score X. And you're probably like, well, what's that do? That's weird. If you don't understand this, that's okay. I tried. You can look this up more on your own. There are great Khan Academy videos on this. If you really, really want to understand like natural logs and stuff like that. I'm going to admit to you right now, this is not my strongest mathematical calculation suit. Like me and natural logs, I know what they do, but I don't know them as well as I know p-value or other things. Now let's just look at just some numbers and their natural log transform scores just to see what a natural log transformation does. So I have a score of 2. When I take the natural log of that, it becomes 0.7. 4, 1.4, 6, 1.8, 10, 2.1, 12, 2.3, 14, 2.5, 16, 2.6, 20, 2.8, 22, 3.0, 24, 3.1, 26, 3.2, and 100 becomes a 4.6. So essentially what's happening here is that more extreme values get pulled in to the means. It brings it in. It like takes those larger numbers and brings them in, makes them smaller. It's also reducing the distance between the numbers. This right here demonstrates what happens when you take the natural log of scores that go from 0 to 12. So you can see here, if this was a linear relationship, right? Like a score of 1, 0 to 1 is a distance of 1, right? So if this was a linear relationship between two numbers, we would see just like a line that just keeps going up steadily here in that nice linear fashion. It would cut through all these blocks. Or we could see it here, like a linear line here would just keep increasing, 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 increasing. But with our log, for numbers that are greater than 1, we get an increase, but you see it's not linear. right? It's kind of sloping, it's kind of curving, it's not as extreme. This is where those numbers come from, right? This is a visual representation of what the natural log does to the numbers 0 to 12. Right, you can see that, and then you can see it kind of steadies out, and it's just going to kind of keep going and steadying out, steadying out, steadying out, steadying out, so that extreme numbers get transformed into less extreme numbers in a data set. That's what happens. Now, I think it is interesting that the numbers between 1 and 0 become negatives, okay? And they go on, you can go out to 0.00000. It's just going to go on forever, okay? But essentially, what's happening here is that the extreme scores are being made less and less and less extreme. So we're pulling them in, and these transformations are known to make data sets more and more normal. But that is what the natural log does. We use it. You can see this when you have outliers or extreme values or non-normal distributions. This transformation is going to make those numbers more likely to be normal. So essentially, that's why we're doing what we're doing. This is a visual representation of it. So we have to transform our data, rerun the other thing I didn't mention, I want you to notice that you cannot have a log of a value that is 0. This line never touches 0 or less than 0. So if you have a data set like we currently do with zeros or negative numbers in there, you have to add a constant to it to get rid of the zeros and negative numbers before you can take the log of those numbers. That is just a fact you're going to have to learn. Oh, sorry. Don't know what's going on here. It's not being my friend today. Okay. I'm going to show you this in Excel in the Internet QQ plot, and then I'm going to show you it in SPSS again. So, I'm going to escape out. I'm going to make sure I have my data, which I kept up here. That's why it was there earlier. I'm just going to open a new Excel file here. And so first thing I notice, I have zeros in there, but I have no negatives. So I'm going to create a new number. This is just my data. I'm going to create a new data column that's data plus 1. And that just simply equals this plus 1. You could do this by hand too. I'm just adding 1 to it. I'm doing that because you cannot find the log of a 0. So, that's just how that works. And then now I'm going to find my log natural of data plus 1. And that simply equals the log natural of that. And you can see the log natural of 1 is 0, and you have these numbers here. Now, what I want to do is check to see if my normality got any better with the log transformation. So I'm going back to that internet website that's linked. It will be linked also on our website directly, and also in this PowerPoint. But I put in my new numbers. These are all my log transform numbers, and I hit compute. And I can already tell that my normality has improved. I'm going to screenshot it just to prove it to you. I'm going to try to just go ahead and get it closer here. And what you'll see here is that these numbers aren't really going away. These are my zeros and my ones from earlier. You can see that, right? But now they're my ones and my twos from my current. Well, they're log transform now, so they're different. But still, these are not going away. Those aren't going to fit the line. So I'm looking at the other numbers, and I'm looking at these numbers right here, these 3 dots, right, on my QQ plot. They are further away than these 2 dots. So I've improved normality. And so now, have I improved it a lot? I've improved it enough for a small data set like this to demonstrate my point. Okay? But, from that, I'm going to want to calculate, how do I use these log transform numbers? I'm going to show you that in the next slide after I show you how to do the same thing in SPSS. So I'm going to click open SPSS and, remember, so I want to add 1 to every single variable. So I'm going to compute the variable. You can see I've been playing around with this, but I'm going to call it stress plus 1. And that simply equals stress plus 1. So what it does for every single observation, and I don't know what that's doing. Yeah, I don't know what I just did there, but that's okay. We'll figure that out later. First, it just added 1 to my numbers. And then I also want to create the natural log of that stress plus 1 variable. So I'm going to compute a variable. If you click on the arithmetic function group, you'll see ln. That's your log natural. I shove it up there. I want to get the log natural of all my stress plus 1. Cancel. I want to create a new variable called stress plus 1 log natural. So it's the same. So I like to name my variables very explicitly. If you even wanted to, you could do that. So I'm going to click OK. And then we have this new variable. If we check with Excel, they're going to be the same. There's going to be some rounding differences, but nothing too major. And I'm going to go Analyze, Descriptives, QQ-plot. I'm going to remove my old stress variable, put my new one in there, click OK. And then I'm going to look down for my new QQ-plot. Remember, they give us stuff that's not valuable. I'm going to go ahead and put this into my Word document to compare. Maybe if I make it bigger, we'll be able to see it. Okay, I'm going to shrink this down a little bit. Hope the other one comes up. Shrink this down a little bit. Hope it comes up. And you can see I screwed up there, but even when looking at it, you can still see the same trend. See, this number is this number, this number is this number, and then this number right there is that number. So it shows the same thing as the previous distribution. I just happened to screenshot it at the wrong time. Now, screenshot on a Mac is Control Command Shift and 4. So Control Command Shift, press the 4 button, and you should be good to go. And then you can it copies it to the clipboard and you can paste it. But here I would argue my transform numbers really, really, really help out. They really worked out, made it a little bit better. Is it perfect? No. If I was really worried about this, I could find a different transformation. But remember, it's not that great because it's a small data sample, so it's kind of hard to tell. So don't worry about it too much, but I do want you to check for normality in your data sets. Now let's go. So we just finished this. We've checked that our normality improved through our log natural transformation. So you're like, well, okay, what does this do? Well, you're going to run statistics on your log naturally transformed numbers, which creates a headache for two specific calculations, reporting our means and our standard deviations in our reports. So essentially, what we have to do is we have to back convert our log natural transformation into normal numbers. And how this works is, we calculate a mean of our log transform numbers, and then we convert that mean back into numbers on our raw data scale. So essentially, we got to go back to this formula. The log natural of a score x equals a. So that's the a is our log natural transform number that we saw in Excel, that we saw in SPSS. Okay, and so essentially we use the formula e to the 8th power equals x. So what you're going to see is that one of our means, our mean for our data set is 0.69 in terms of log naturally transformed numbers. So what we have to do is we have to solve for x in the equation. E to the 0.69 power equals x. Remember, e equals 2.71. So 2.71, so forth, to the 0.69 power equals x. We can use math to solve for that. X equals 1.99. Remember, we added 1 to this to the entire data set because we had zeros in our data set. So now we have to subtract 1 away from that 0.99 to get a raw score of 0.99. So our log transformed mean, our mean of our log transformed numbers is 0.69. When we convert that to numbers on the scale that our raw scores was in, that mean is 0.99. Now I'm going to show you where these numbers came from so that you are not confused. But essentially, I have another Excel sheet that allows you to convert from natural log numbers back into the original scale. Now, this box right here just creates the natural number. This box right here just looks at the log natural we're trying to convert, the log natural number we're trying to convert. This number right here does that conversion stuff where we had e to the a power equals x. This is just solving for x. This notes what constant we added to our data, and this subtracts the constant out. You can see. Okay, so let me that's what the cells are doing. So what's going on here? So first things first, I calculated an average of my log transformed numbers, and I'm like, okay, my log transformed average is 0.67, okay? So I'm just going, what is the log natural number I'm trying to convert? That is going to be 0.67 right there, right? I did add a constant of 1 to there. I plugged that in. I already have it in there. And then what happens is that my mean gets converted to the mean in the original number scale. So my mean is 0.99, right? That's my back converted mean of the log natural number. So that would be the mean in my original data set if it was normally distributed. So let's take a look at what my mean in my original data set was. It was originally 1.3, okay? And our new mean, after we remove the errors with normality, is 0.99. So what you can see here is that if we did not correct for normality, we would have a quite drastically different signal, right? One that's affected by the lack of normality. Our signal's, it's quite larger. It's 33% larger than our estimate of signal after we correct for normality and back convert it, right? So this would be the mean that we would report. We would, in our report, say we used a log natural transformation to take out the lack of normality. From this, we back converted our log natural mean into traditional raw scores, and we found that our mean most closely represents 0.99 on our original scale. Now we can do the same thing for standard deviation. You can see this is the standard deviation of the sample. That's mostly what we're going to use. So I let Excel calculate my standard deviation. And then I'm like, okay, let's back convert this. I'm going to click on the cell. My 1, I'm still dividing by 1. And my estimate of standard deviation is, I'm just going to say 0.77. But you can see it's right here, 0.768, blah, blah, blah. All right, now I'm going to do the same thing here. Standard deviation. This is of the sample, of all my sample observations, right? When you do not correct for normality, the estimate of your noise is nearly double the size. The estimate after we correct for the normality failures. Remember, this is the foundation of all stats. Means are signals, standard deviations are noise, signal and noise. When we do a normal, convert it to a normal distribution with the natural log and back convert, our estimates are simply better. They're more true, and we've reduced error in our estimate because guess what? There's error in our estimate because we had non-normal data. So all we're doing right now is cleaning up our estimates of signal and our noise. We're cleaning up our descriptive statistics. when we're going to use these in the future, I'll show you in future videos how to use these. Okay, but essentially, that is all we are doing for today. So now we've transferred our data, we've back converted it to the original metric to see how much that lack of normality affects our estimates of our means, how much that lack of normality affects our estimates of standard deviation or our noise. And it has a drastic impact in this specific data set. Now that is our lecture for today. I have a simple assignment for you. I am going to post just one column of Excel numbers. I want you to clean it for impossible numbers. I want you to clean it for outliers. I want you to clean it for normality. And it will have outliers. It will have impossible numbers, and it will not be normal. All right? And then at the end, I want you to back convert your mean and standard deviation of that one set of numbers into the original raw score numbers, just what I just did, the raw score scale, right? Not the log transform scale, but the original scale that the numbers were presented in. That's it for today. We're doing great. I fixed up. I hope this makes sense. If you have any questions, just ask them at the beginning of class. I don't think class is going to take us that long as you know how to use here's what you need to really take away. Use my Excel file to get rid of outliers. Use the methods from either SPSS or from Excel and that internet web page to check your normality. If you have non-normal data, transform it using the natural log, using Excel or SPSS. And then once you've done that, calculate the means and standard deviations of your log transform data set and back convert using my other Excel file. That's all you need to know how to do. Right? This is one where I'm not going to test you so much. The MAD is using a specific method to test for outliers. I've described that method. You can just cite the paper I showed and say you're using that method. If you want to understand it, come talk to me during my office hours. We can talk more. And then the other form is just we're checking for normality, and we're using one transformation, teaching you only one transformation to fix normality. If you really don't have normality in your real data set and the log transformation doesn't work, come see me. I will help you out. In fact, when it comes time, let me know when it comes time for you all to do your data analysis. I will sit in a room with you and help you out. I will get a room for us, and we will sit, and I will help you out with your data analysis, okay? So ultimately, this lecture's done. I'm excited. This is the last day before we actually start null hypothesis significance testing. And I will expect you to clean your data from now on. So yes, this is a pain in the ass. I acknowledge that. But it gets us a better estimate of signal and a better estimate of noise. Why wouldn't we do this? All right. Lecture out.